Hello everyone, today we have a practice problem here of going from this alkyne undergoing acid catalyzed hydration and how we get two ketones out of it, right? Because you may be looking at this, you're like, get two ketones, that looks kind of weird. So let's explain what's going on here. You can try the mechanism yourself if you'd like to pause the video, grab a piece of paper and try it out. If not, I'm just gonna get started here. So let's redraw our starting material, that alkyne. So the first step here is going to involve the mercury. The mercury is really going to get this party started. So mercury is an ionic compound here. We know that the sulfate is a -2 charge, but that makes the mercury +2. So -2, +2, so mercury has a +2 charge, but it has a lone pair of electrons, and this is important because those electrons, they reach out, they attack one of the carbons. Doesn't matter because each side is equally as substituted, making the resulting carbocation on the other side equally as unstable or stable. So this then makes these pi electrons give that mercury a hug, and it gives rise to a molecule that I will draw now. All right, and now for assigning charge, if mercury gave 2 electrons and gained 2 electrons, the charge doesn't change. So we have a +2 charge, or 2 +2 charge. Alrighty, and for what comes next, we know that a 3-membered ring is highly unstable and a nucleophile could attack. Out of the 3 options that we have here, we have our acid, our mercury salt, or we have our water. Now, water kind of sticks out to me as being the nucleophile here, and that is actually the case. So these electrons, it will attack either side. This is what explains this here, right? It doesn't matter which side it wants to attack, it's equally as substituted, and it doesn't really matter. So it goes like this, and these electrons get dumped over there. Alrighty, and the resulting compound we get looks like this. All right, oxygen has a positive charge, and we know oxygen does not like that. Oxygen hates being negatively charged. So some sort of base is gonna come in here and steal that hydrogen. And the one that will most likely do this, again, is probably water, right? Because the conjugate base of a strong acid is a pretty terrible base. SO4, again, it's not really gonna want to take a proton, but H2O can do it to an appreciable amount, acting as a base, so it's like, yoink, give me that. And the electrons are dumped on the oxygen. So now we have this molecule here. And now this is neutral. Okay, moving on. Let me just make sure the screen can see the next step I'm about to draw. Okay, it looks good. Now this is where H2SO4 comes in handy. It's an acid, so it's going to get hydrogen's gonna get picked up by the pi bond there. That electron density is gonna be like, you're pretty cool, man. And it's gonna add to the side. Oh my goodness, I cannot draw my geometry to save my life, okay. It's gonna add to the side with mercury, leaving a positive charge right there. All right, I'm gonna just redraw it down here. Hopefully you can think of the next part of the mechanism. And then like that, and have that carbocation right there. So what's going to happen now is that mercury is just going to leave. It does not want to be there anymore. So now we have an enol. We know that a ketone is more stable than an enol, so we're going to have to go under tautomerization. So how we do that? First part is we will do the same step as right here with H2SO4. I'm going to simplify it and just say it's a free-floating proton. So again, that pi bond picks it up. It's going to want to arrange itself on the less substituted side to give rise to a more stable carbocation. So we get this here. That's a positive charge, no bueno. How can we deal with this? Well, we have an acidic proton there, and if we could somehow make this a double bond, I think that would be pretty stable. So let's go here and have our water molecule. Our water molecule is going to reach out and steal that hydrogen, and those electrons are going to be dumped on the oxygen. Oh, my goodness. All right, so we have a negatively charged oxygen and a positively charged carbon. Well, the two are going to look at each other and be like, you're negatively charged, I'm positively charged. Well, can't we just share some electrons and be neutral, right? Because neutral atoms are more stable. So oxygen is like, okay, I'll give you some electrons. And we get our final compound, a ketone. But remember that this also will happen for this one here. We got that product, but how do we get that one? Well, in this step here, we just attack that carbon, right? We attack, oh my goodness, I am so silly, guys. It goes like that. Had the arrow on the wrong side. Electrons are dumped on the mercury. But anyways, the water could attack that side, and then the resulting mechanism would just occur with the water being here, right? And then downfield reactions, it just leads to this product. So quite simple. Hopefully this mechanism makes sense. This is hopefully the first time you're getting into the more complex of the mechanisms. So hopefully you guys enjoyed and found this helpful. I'll be looking to make some more videos soon, maybe another example of this. So have a good day, everyone. Goodbye.